Hello everyone, welcome to the 22nd episode of Math and Beyond Analysis podcast. Today we are talking with Andrea Caputo, and by the way, I changed my location. I came back home in Italy, and so I will be recording a couple of episodes from here. You may hear from my voice that I have had a graduation party yesterday from a friend of mine. So I have a little bit of low voice. You will excuse me for that. So as I said, today we are going to talk with Andrea Caputo. He's a senior fellow at CERN. So in Italy we say tanta roba, which means a lot of stuff. He has been a postdoctoral research both at the Tel Aviv University and at the Weizmann Institute of Science simultaneously. Then he did his PhD studies in Valencia, and then before his graduate studies, so master degree in Italy, in Rome, as well as the bachelor degree in Calabria. So today we are talking about new physics beyond the standard model. I am greatly excited because I have met Andrea at a seminar conference, sort of a seminar that was organized by Grappa in Amsterdam, and he was invited to talk. He gave a talk. He gave a presentation, and I stopped talking with him at the time slot that you can book, let's say, sort of a meeting, a talk with a guest. And I think a nice conversation will come out. So I will send him the invite and I will see you shortly. Okay, so hi everyone, welcome back. Here we are with Andrea Caputo. Ciao Andrea, thank you for being with us.
Hello everyone, thanks for having me. Actually, it's a pleasure, my pleasure.
So as I said, you are now a senior fellow at CERN, which is, I believe, an exciting experience, and we may dig into it a little bit later. Now, as I said, we are going to talk about new physics beyond the standard model. And I would like to ask you to start by very briefly introducing, just taking a couple of minutes, explaining what is the standard model and why is it our best theory of the physical world.
Exactly. So okay, let's do it brief, but in brief, actually, the standard model is basically the theory which describes really our universe at the very microscopic level, okay? So at the very fundamental level, so I would say. And so describe the interaction among the constituents of the universe, okay? Which are basically, for example, electrons, what we call quarks, our photons, and all the particles that basically constitute at the fundamental level all of our world. The standard model is basically a theory which describes the content of matter. So it defines the particles that we have in our world at the macroscopic level and the interaction between these particles. Okay. So for example, the standard model regulates with the standard model, you can write down all the interaction, for example, between electrons, the interaction between what we call quarks, which made, for example, protons that you may heard of. And so it's a set of rules, right, which define all this interaction, and is a very, very successful model. As you also said, is the best theory that we have. We really can explain most of our universe in this case. He had a lot of predictions that then were verified. The last that I want to mention just briefly, because I'm here at CERN, is the Higgs particle, right, which is one of the missing pieces of the standard model, and was actually discovered a little bit more than 10 years ago here at CERN. And it's basically the particle is a gauge boson in technical details, which also gives the mass to most of the other particles. So the standard model, in brief, is this one. It's a collection of, a description of the content of matter in the universe and the rules of the interaction between these particles.
Okay, today we are talking about new physics beyond the standard model. We said that a standard model is our best theory of the world, but we also have to say that we have some problem because there is something that we cannot explain. We have some current limitation. First of all, is gravity. Why is gravity not included in this model? what problems arise when we try to do so?
Exactly. So like, so it's a very good question. Like, so first of all, let me stress that when I talk about the standard model, one also typically would like to talk about what we know as quantum field theory. Okay, and quantum field theory is basically the mathematical framework in which the standard models plays, right? And so in which the descriptions that we're talking about are set up, right? And basically, quantum field theory is just a fancy way to say relativistic, in which putting together basically quantum mechanics that you probably also heard of, and is at the basis of a lot of the thing that we use, like transistors or whatever in technology, and then also like relativity, but like special relativity, the theory of Einstein, so kind of like the relativistic version of non-relativistic quantum mechanics. So this is what is the frame of quantum field theory, which describe the standard model that then is applied for when I talk about standard model. On the other end, when we talk about gravity, right? At this point, the notion of gravity and the theory of gravity is basically the theory of Albert Einstein, right? Which is basically based on the fact that bodies with a mass like affects the space-time and shape the space-time. So it's kind of like a geometrical description is the description of gravity that we have at this point, right? And so it's very different than even at, from the surface to a description like quantum mechanics, in which instead you talk about microscopic particle and states and also different mathematics if you want, right? So then what you can try to do, you can try also to apply quantum mechanics, so technically to quantize gravity, so to go to the theory of Einstein and try to describe it also in the terms of quantum field theory. And when you try to do so, actually you realize it is not that easy. And basically at the technical level, you start to encounter infinity and quantities which are ill-defined, right? And so that's one of the issues. And to be honest, I'm not an expert of let's say the theory of quantum gravity, but of course, just what I want to stress is that the idea is that in the standard model, as I was saying, we describe all the interaction between particles, but another interaction between particles that we know for a while is gravity, and that's not included. So we would like at some point to do so, but at this moment, it's not clear that that's possible at all, right? So it's just difficult, technically difficult, because within quantum field theory, you start to encounter a theory which is basically it's called non-normalizable. So you will have infinite terms when you try to include gravity, and that's basically ill-defined and doesn't give you any, real prediction, okay, like in the framework of quantum.
Okay. Can I ask you sort of quite speculatively, and I don't want to expose you, but what do you think is our best theory of quantum gravity at the moment? Which, of course, we know that there is not a definite one, yes, but what do you think is the one that gets closer?
Well, I think that, like at the moment, everyone, not everyone, but most of the people would probably agree that the best hope for a while has been string theory, in which basically you try to get, like you can try to get rid of these infinities and stuff, like saying that the microscopic entities are not like say particle, but are these strings that vibrates and then give rise to all the phenomenology, right? Of course, also that comes with some difficulty. You have to have like a lot of like other dimensions in which we live, and then gets compactified, and we don't see them, but they are there. It's very difficult to test, right? But if I have to say at the moment within the theory that I see around, like look, quantum gravity and all the stuff, string theory seems the one that seems more like solid, on which people invested a lot of time, also the mathematics. But yeah, I mean, from here, this is my personal opinion to say that, that will be the theory, that's a huge step. But at this point, the string theory, I think that is still the best option. And this was also the opinion, for example, until a few years ago, at least when I heard some of his interview of, like, for example, Steven Weinberg, that passed away 1 year ago, and he was a giant of our field. And although he never really worked in string theory, he was always saying that it was still the best hope for a unifying theory, because it's a beautiful framework, it's a mathematical beautiful framework, right? So that's, I think, is still our best theory at the moment.
Okay, given the last 100, say the development at accelerators of the last 100 years, do you think in the next 100 years we may hope for a hint of experimental evidence for string theory?
Well, that's also a good question. For string theory, I would say which is that is very, very difficult. I mean, I'm not an expert, so I don't want to say something, but even if I think just also at the very naive level, right? You can push, let's say, 50 or hundreds of years with colliders, and let's say that we build another colliders like they're discussing at higher energies, right? Then you can reach like tens of TeV or whatever. But when we talk about gravity, we are really aiming for a scale which is very, very large, which is the Planck scale, right? So just to give you an idea of the scale of the game, the Higgs, right? So the actual LHC and whatever, so the particle that we discovered 10 years ago, the scale is hundreds of GeV, where GeV is a unit which means 10 to the 9 electron volt, right? So hundreds of GeV. When we talk about the Planck scale, which is basically the scale which sets the interaction of gravity, basically the Newton constant can be written in terms of this scale, right? The scale of the Planck mass is basically 10 to the 19, around 10 to the 18, 10 to the 19 GeV. So we are talking about a gap, you know, of 17 order of magnitudes, right? So of course, there could be theory in which even a smaller energy, you have sign of other particles that appear and, you know, may be connected then to your theory, right? But an evidence of string theory, especially for this, like, is very difficult. There may be at colliders, there may be possibility to see something in cosmology, in cosmological imprints, just because if you imagine that, you know, with cosmology, imagine that just very naively, imagine that with cosmology, you can probe the very first instance of the universe, right? And the theory, the moment that are called also inflation, right? So if the scale of inflation is large enough and you see something, you know, you can exclude maybe some theory, right? Or like, you know, like that are related to string theory. Proving, in my opinion, is always very difficult because you can always like hook up something to, you know, to say whatever. So yeah, in short, the answer is at colliders in the next 100 years. I don't think that we will have any, you know, definite hint of string theory. And but you know, again, like I want to stress that I'm not an opinion.
Okay.
Otherwise,
Sure.
it's my opinion. Otherwise, my colleagues will kill me. But
Okay, maybe if we start cutting 10% of the yearly budget expenditure for military expenses, we may have some.
yeah, but
further.
even that, I mean, because at the end of the day, if you think about it, like on the you know, like on the huge global cost, you know, when people also look at colliders, it's been like it's a huge, you know, huge cost. It's large cost, but not huge, right? Like so but even if you add some more, and I think that also another thing that people sometimes like or underestimate is that every time that you aim for something for the next step, there are technological difficulty to go to that next step, right? So it's for sure something that independent of the money or stuff, it should be in any case go by step and by grades, right? You cannot go from, let's say, TeV to 10 to the 6 TeV, right? It's just unfeasible, right? Also, like step by step, you develop the technology. At CERN, for example, we developed, you know, like amazing superconductors. At the very beginning, we had to develop the internet, right? So the web was developed at CERN just because they had, you know, like to exchange a lot of data that they didn't have before, right? So also this, like, just one thing that I want to stress is that you know, you hear this is also my opinion, but you hear a lot like around you know, yeah, maybe we don't have to build a new collider or whatever. I just think that not building new colliders and go on and on, it will be also very, very bad and also very selfish for people. Because if at some point, you know, you just stop doing so and you stop exploring, although we know that there has to be something else because the Planck scale is so high, so it's very unlikely that in between there is nothing, right? If you at this point you say you stop, right? And then you want to recover like in 100 years, right? Because maybe you have some incidents, okay, let's build a collider. That's a disaster because in the meanwhile, you lose all the expertise, people stop working on that, technicians stop working on that. So like one should really think more broadly about science instead of just saying, oh, look, don't do this collider, do something else, right? Because then if you stop something, then it will be very difficult to recover, right?
Okay. Okay. Science is a collective effort. Okay.
Yeah.
I would like now to move on to another gravity-related problem, which is the hierarchy problem. What is this problem, and why do we think this is a problem?
Yeah, like so the hierarchy problem is a problem which has been driving also like for probably 45, 50 years, high energy theory. And the problem in some sense is simple. Like, as I say, we have the Higgs, right? And I think that, what we talk about was a nice introduction, because I said that we have the Higgs, and this Higgs has basically, the scale of this Higgs is like hundreds of GeV, right? But then, when you do quantum field theory, and so what I mean about the scale is like the mass that we measured of the Higgs is around this value, right? But basically, in quantum field theory, when you do you write down, technically it's written like your Lagrangian and your interaction, right? Then you will have the bare mass of the Higgs, which is just a parameter, let's say, that you have there, right? But then actually given that it's a quantum theory, what you find out is that if you have other particles which interact with the Higgs, in this case, right? Then this interaction will also contribute to the mass of the Higgs, okay? And if you have even other particles that you don't see now at higher scale, whatever, everything will contribute. If they interact, they will contribute to give a mass to the Higgs, right? And when you do the calculation, basically, and you try to ask the question, okay, which is the contribution from these other particles, right, to the Higgs mass? Okay, like also, for example, the top is a quark, right? Which is the contribution of this other particle to the Higgs mass at the loop level, which is to say the quantum level, okay? When you do this computation, basically, at the end of the day, you find that this correction to the mass is proportional to some number which depends on this parameter, like the mass of the fermions or the Yukawa coupling, technically, and the scale, okay, let's call it lambda, up to which the standard model or the theory, the quantum field theory that you're talking about is valid, okay? It's called the cutoff, right? So, saying in a simple way, the fact that we already know that at some point we have the Planck scale, right? So there is another scale, right? And the fact that we know that the standard model describes the low energy theory is basically telling us that the contribution to the Higgs mass, okay, coming from this, lambda, right? This cutoff, right, would imply that if this cutoff is above the TeV or 10 TeV, if these are the Planck scale, basically, for example, imagine that this cutoff is the Planck scale. So we are saying, imagine that we take our standard model and we extrapolate it up to the Planck scale, up to string theory scale, right? This will be the cutoff. Then what you find is that basically the Higgs mass, the one that you measure, should have been much, much larger than it is, just because, as I told you, this quantum correction had in such a way to depend on this cutoff scale, right? And so this is the so-called hierarchy problem. So it's the fact that basically if you do the computation at the quantum level of the Higgs mass and you imagine a cutoff scale which is large enough, right? And it has to be large enough. For sure, for example, it has to be beyond the TeV or so, because with the LHC and stuff, we saw that until this scale, our theory works, right? So like there are no other particles or nothing. So this is called like kind of the little hierarchy problem. If you then instead you do another step and say, okay, let's extend that to Planck scale because we know that Planck mass exists. That's the hierarchy problem. There's a really huge tuning that you have to have. Okay, so this is the hierarchy problem in brief. But in more brief, it's just the fact that in a quantum theory, the Higgs we know will receive correction that will make the mass much larger than the one that we observe in principle.
Okay. Yeah. Why do you think this is the case that we see?
Yeah, I mean, I know. So first of all, like it could well be that there is some tuning issue, and it could also well be there is some new physics that prevents this, right? So this actually brings me to say, at the beginning I said that the hierarchy problem has been driving like a lot of the also theoretical ideas in the last 40 years, because for example, you probably heard and the public heard about like supersymmetry, right? Supersymmetry is something that will typically a lot of people talk about, have been talking about for a while. And supersymmetry was basically motivated by the hierarchy problem. And it's a very simple concept. It's a very beautiful theory, although experimentally we didn't see any sign of it. We would have expected the standard like supersymmetric model to show up at LEP, was one colliders in the 90s, and also then at the LHC. But still not dead, right? There are versions which works fine. But in brief, the supersymmetry theory, what does is that in the standard model, you have some contribution to the Higgs mass, as I said, right? For example, technically, you do loops, they are called. For example, in this loop, there are the fermions, the quarks, the top, for example, right? Now, what supersymmetry does is that for each particle, the standard model, there will be some supersymmetric partner, which is a particle, which is basically, instead, for example, of being a fermions, it will be a boson, where fermions and bosons are two different kinds of particles that we have in the standard model with what is called the different statistics, right? Their statistics is different, they behave differently in that, how can you put them together, okay? So basically, and when you do this loop that I was talking about, typically fermions or bosons pick up a minus sign of difference, okay? So the trick of supersymmetry, in brief, is basically that if you add particles which are partners, right? And then when you sum this contribution for whatever particle which is giving you a plus contribution, there is the other particle which is giving you a minus contribution. So at the end of the day, all this quantum contribution that I was talking about, they cancel each other, right? And you're left with a bare mass, small mass that we measure, right? So that's the idea of supersymmetry, which I think is a beautiful idea. But then, of course, as I told you, you have to introduce all the super partner particles. And then people have been looking for that and sign of that, and we still didn't find any. So at this point, supersymmetry as string theory is only like a theory, right? So physics is an experimental science. I want to highlight that. And we don't have experimental confirmation from that. But that how is true how we would solve the hierarchy problem.
Okay, actually, I think I can make. I probably am risking it to correct you, because I've heard the fact that string theory is actually shouldn't be called a theory, because a theory is something that is experimentally validated. So it should be the string proposal.
Well, that's I think that also like is a kind of like semantic, right? Because a theory is something that at least like, you know, for how I see like a theory is something that aims to explain the real world, right? And the string theory aims to do so, right? Because string theory aims to explain why gravity works like it does, like why quantum field theory works like it does, but in a unifying framework. And actually, I want to say also that string theory at the very beginning was not born to explain quantum gravity. The idea of string theory was born to explain QCD, so strong interaction. When Gabriele Veneziano here at CERN actually started to write down, what then would have led to that, right? It was thinking about strong interaction. It was not thinking. So it was really a theory for experimental stuff at the time, even at CERN. And also now the goal is always that. So I would still call it a theory. What I would say that at the moment is only a theory, like a theory, right? While when you talk about the standard model is the theory of like particle interaction, because we know it works. But even, and this I want to mention again, even if you read the paper by Steven Weinberg, in which basically theorized the standard model, when he theorized the standard model, he was explaining some experimental facts and stuff, but he didn't believe the real world was that. He said at some point in the paper, these models have too many parameters to be taken seriously, something like that, because there are the Yukawas, the stuff. But at the end of the day, it is the theory, experimentally confirmed, beautiful. So my point is just that there is always a step in which your theory will not be still proven. The important thing is that you have a scientific goal that you hope to at some point measure, right? The point with string theory, I guess, that just this some point when it's going to happen is not at all clear, if possible at all, right? That's I think the main problem.
Okay. Regarding supersymmetry, can I ask you, how do we experimentally validate it?
Yeah, like you have to to find these supersymmetric particles, right? So you
How
have
do you?
this like, for example, at colliders, there was always the hope, for example, when the Higgs, when the LHC was, turning on to find the Higgs or whatever, the hope was also to try to discover new particles. And some of them, one of the best hope was supersymmetric particles. Because basically what you do, one that you write down the theory, right, you precisely know how these particles interact with the standard model. So in principle, when you smash together protons at the LHC, right, or when you smash electrons at lepton colliders or whatever, you know what you would expect. And in some of the theory, you would have expect to see a signal that then that was associated to these superpartner particles, the presence of the superpartner particles, and this signal we just didn't see, right? But there are people have been looking for it, people that will be looking for it, and so it's still not, it's just something that I guess, for what I see, people dedicate a little bit less effort and time, because I mean we look for that for 30 years, we didn't find any. So at this point, also the theory is set in some sense. So at this point, just we have to wait maybe for higher energies, but there is, in my opinion, not. And again, I take my own responsibility. I think that you can see a huge decrease in people working on that, just because at this point there is not much to do, I would say. But maybe in the future with new colliders, yes.
Okay. Do you think supersymmetry is the best theory for explaining the hierarchy problem, or are there any other proposals we should?
There are other proposals like extra dimensions, also composite Higgs, in which like the Higgs is not an elementary particle, but is a composite particle, and then in that case you can also solve the strong city problem. Is probably the one that I like the most, just because the mathematics is very elegant, and I just think that it's beautiful, and it gives you precise prediction, but also the others, right? But for me, it's the best. But it's for just my taste, right? There are other proposals, like not by any means supersymmetry is the only proposal. I mentioned just a couple, but there are many proposals. There is another proposal that, for example, is called that gained a lot of interest. It's called the relaxion, who was proposed some similar idea by Hubbard in the 90s, and then people from Johns Hopkins and Stanford, Berkeley recover in 2015. And it's basically just the fact that you have a dynamical explanation over cosmological time on why the Higgs is what it is now. And so that also aimed to solve the hierarchy problem. But still, also that is not that elegant, in my opinion. Like supersymmetry is still the best. Like I don't want to say that whatever is elegant is true, right? But I want to say, like, I don't know, if I have to bet, I would bet more on supersymmetry than the others, but that's just my own, my own taste.
Okay. Talking about Steven Weinberg, he wrote a book about called The First 3 Minutes, which I believe also covers the concept of inflation, if I am correct. And I would like to connect here to the concept of inflation and something else by asking you, why is the standard model inconsistent with our current cosmological model, Lambda-CDM, which predicts to have that there is something as called dark matter, and we can extend it even to account for inflation. Why do we have some problem?
Yeah, so first of all, I would just lightly correct you in the sense that it's not that the standard model is inconsistent, right? I mean, it would be inconsistent is if like whatever we see with the standard model is in contrast to whatever we expect, or like we have seen in cosmology or stuff, right? Well, this is not the case. It's just what I would say is that from there, and now I will explain better, the standard model is incomplete, right? I will tell you that basically it's very easy to extend the standard model. It's a bit like, like imagine, I want to do this example very quickly. When Einstein invented his theory, right, of general relativity, it was not really, it was not really that Newton theory was inconsistent, right? Newton theory was working perfectly fine for something, right? But if you wanted to do a next step, right, and study something else like lensing or other stuff, then you needed a better theory, right? But the general relativity theory reduces to Newton theory in some, in some limit, and for some observable, Newton theory is enough, right? So in that case, you would not say that Newton system theory was inconsistent. It was just not complete, right? Not the complete theory, right? And in the same way, the standard model is a very beautiful, is a nice theory. But when you go and study the evolution of the cosmos, you realize that you need some ingredients that they're not present in the standard model, and I will give you a couple of examples. So first of all, one of our best theory to explain some of the puzzle in the universe is inflation, which is to say, from the, like there was an initial moment of time in which the universe was expanding extremely fast, right? And this would solve some of the issues that we have, like the horizon problem or the flatness problem, which are some problems which arise from observation in cosmology, right? Then on the top of that, at the end of inflation, then it starts the usual Big Bang story that we know, okay? That gives rise to all the elements, for example, hydrogen and helium, and then all the evolution to the formation of large-scale structures, galaxies, and all the things that we see. And in that case, we know that, for example, we have to have dark matter, because if there was no dark matter, then we cannot explain most of the observation that we see. We cannot explain the world in which we live. Basically, we would not be here, right? And then there is actually also dark energy, okay, which is now the universe is expanding, it's accelerating. Is actually accelerating, is always expanding, but with an acceleration. And so there is some component which we call dark energy, which behaves in such a way to make the universe accelerate. Okay. And for example, let's talk briefly about dark matter. Dark matter, we think that is a new particle that has to be there. We have many indications that is a new particle, although there are some people that still think that you can modify gravity or whatever. I don't think this is the case, because there are so many observations also in the early universe, in the late universe. The easiest possibility is dark matter is a new particle. That's it, right? Very easy. You can explain in new things.
Why do you say so, that it's the easiest possibility?
Well, because basically, I can give you a couple of examples and to justify this, right? Observational. So one of the first way in which we knew about dark matter was the fact that astronomers, they look at galaxies and they measure rotation curve of galaxies, right? They measure rotation curve of galaxies, and basically what we saw that there was an error there, in the sense that you could map the mass in that galaxy that you see with your telescope, right? Visible. So we would call this visible matter. But then if you track how stars move, that would not basically coincide. Basically, like you would, if you apply just Newtonian dynamics, okay, and then you would see that they just don't match. A very easy possibility is just to say, okay, look, we can put other matter in there, which is dark matter. We just don't see it, because this stuff, you see the matter, how much is there, and then you do these fits, right? And then they don't agree. But then let's see that now I put an halo of dark matter. We don't see it with our telescope, but it's there, right? It's actually, gravitational interacting. So if you do that, you explain very easily the rotation curve of the galaxies. You explain also easily measurement of lensing. Lensing is how light deviates, right? And basically, you also have in those measurements, you have inconsistency in the sense that if you consider just the mass that you see, right, the lensing that you get is too much. So you have to put other mass in there, right, for example, and similar thing. Another thing that is very important is that we measure CMB, which is the so-called cosmological background, cosmic microwave background, the cosmic microwave background, right? Which is the light basically from the Big Bang. And we measure anisotropy in the CMB, right? And basically we can explain CMB measurement only if we assume, or the easiest way, if we assume that there is dark matter, which is this stuff that interacts very weakly with the other particles, right? So this is why it's dark, right? It doesn't interact much with photons, for example. Then we can explain CMB anisotropy very well, in a very cheap way, very simple. It's just another kind of fluid which is there in the cosmological evolution, right? When you try to do so it's a very cheap option in the sense that if I give you like a mass which is just interacting very weakly, but it's there, right? You explain the CMB, so the cosmological evolution, you explain the rotation curve, you explain lensing, you explain other stuff like palette clusters, or there's another probe of dark matter, or like at least like the fact that we are missing something. And so it's a very economical possibility if you want, just a mass. That's it. Then you can ask if it interacts with the standard model or not, but you can put a mass without interaction at all with the standard model. That works, right? And that explains basically most of the observation as far as I know. If you want instead to modify gravity in such a way to explain all these different observations, it's actually very difficult. For example, if you want to explain the rotation curves, it's actually very easy. You can just modify Newton's law in a kind of parametric way. This is how theory of modified gravity were born, MOND. But there are two problems. First of all, embedding this theory in a consistent framework, like quantum field theory framework, is also very difficult. And you also always introduce new particles. And second of all, within this theory is it's not basically typically impossible to explain CMB, early universe. So this is why I think that dark matter is just a very cheap possibility. Some people don't like it because they want to be, and we have to be open. People have been trying to do modified gravity. It's not that they didn't try. It's just that typically you have a lot of difficulties with that. While dark matter, of course, the main difficulty is that is evidently difficult to find, right? Because it's very, elusive. But all these as you said before, also a theory should describe something, right? Then it's just a description, right? But it's a very beautiful description, just a new particle, that's it.
Okay, and how are we trying to include it in our standard model, or let's say some theories beyond the standard model?
Very beautiful, like very nice question. So the point is that, the first question that you can ask is that actually, is there a possibility that some particle in the standard model do that, right? And for example, for a while, people have been trying to use neutrinos as dark matter, because neutrinos are a particle of the standard model, and they're actually pretty elusive too. They took since their theorization, they took 15 years to be discovered. They interact very weakly and whatever, right? However, then people realized that basically that cannot be, because also that would be inconsistent with the large-scale structures. Just because if neutrino was a dark matter, they would have been produced in what is called warm dark matter, because they are light enough to be produced in a warm state in that case, okay, within the mechanism of production of neutrinos in the standard model. And basically, this would have erased structures on some level, and basically this is we know now that it's inconsistent with cosmology, with what we see with galaxies and stuff, right? So what we have to do, as you say, you typically have to extend the standard model and include some other particle, which can also be a dark matter candidate. And one of the one motivated candidate was the WIMP, which is weakly interacting massive particle. Is a motivated candidate because his scale is supposed to be around the TV, around the weak scale. It interacts with particles weakly, within weak interaction, right? Like neutrinos do, but having a larger mass. And actually, it's very easy to produce it in the universe. If you start with a standard model bath, your particles, it's actually very easy then to, and dark matter, then you start to what is called freeze out. It's very easy to end up with the right relic abundance of dark matter. So that was is a very beautiful possibility. People have been trying to look for it. Until now, unfortunately, we just have null results. So all the experiments for WIMPs have been now, giving zero results. So we just have bound. But that's, for example, a possibility to extend the standard model. Another possibility is the so-called that I've been working a lot also recently about on it, is the so-called axion. And the axion is also a very good dark matter candidate, very easy to produce, because the axion is a particle, is a boson, in technical detail is typically a pseudo-Goldstone boson. And what is nice about the axion is that typically for a lot of parameter space, so to say, a lot of masses and couplings, if you just put an axion in the universe in which we live, that at some point expand and whatever, right? Actually, in many cases, unavoidably, you have the axion to compone a large fraction of dark matter. So in some sense, also that is very economical. You just have a new particle with a mass, a coupling, and that's it. You can do it very easily. So that are, for example, two possibilities to extend the standard model to have also dark matter candidate. But there are many others. People have been talking about sterile neutrinos. People have been talking about dark photons. People have been talking about many different candidates. Right? It's not that difficult. The difficult part again is like then to try to detect this new particle and so prove that that's dark matter, right?
Okay. Again, I want to pick up from what you said before. I want to keep it going for the rest of the conversation. What would you say? I'm saying, on what particles, on what proposal would you bet your money on if you had?
Yeah, like that's a tough question. Like at the moment, for like for what I'm doing, for what I'm working on, I think that the axions are a particle on which we have to bet for a little while. And then of course, like a lot of people complain, like there are also like famous YouTubers, so to say, that are also physicists that then like some saying blame particle physics or like like critique, but we are pretty open. Like people have been looking for WIMPs for a long time, but that's why I think it was correct. It built how you do. You have a theory. The theory in principle works very well. You try to build an experiment to prove your theory. You have a theory which the theory is well posed. You explain something which is dark matter. You build an experiment. You try to see it, right? You don't. Okay, good. Next theory, right? That was not good theory. This is how science proceeds, right? So we did it with WIMP. We are still doing it because experiments are still running, taking data, right? But for that, basically, we just have to wait and see what happens, right? But now there is the next candidate for which we have to do something similar, in my opinion, is the axion. So this is why I would like to bet in the next few years, let's say, because there are many experiments also in Europe, especially in Europe, but also in the United States coming out, in Italy, in Germany, in France, about finding the axion. Okay, so in the next, let's say, 10 years, there will be a huge effort in trying to see if dark matter is axion, and I would bet on that. Although again, it's very difficult. So it may be, is very likely, actually even more likely, probably, right? Just as a matter of probability, that in 10 years we will be, like without nothing, and then we also have to rethink what we thought, right? But the axion, and I think also is that in a lot of cases, also the axion 2 points is very easy to produce, as I say, as a dark matter, so very cheap to to have it as dark matter, very elegant. And also in some region of the parameter space, you also explain and solve other issues of the standard model that I don't know if we will have time to talk about it. For example, the strong CP problem. So I will bet on axion because it is very motivated. But again, I also want to stress, because this I hear multiple times, like people are wasting time. These are complicated questions, and these are like very fundamental questions, right? I think it is very, very motivated to try to look for dark matter. It is true that at some point you have many candidates, you have to make some choice, and at some point it looks like we are going into the darkness, right? In some sense, like without a goal. But it's not true. We have like some theories, some belief. We try to test that, but that's hard. But we are very open. If we find out that that cannot be, like that we win, or even look what people did with supersymmetry. People try with supersymmetry, but it's not that after LHC everyone was still continuing to work on supersymmetry and that's it, right? Most of the people stopped to work mainly on supersymmetry because there was no experimental evidence, and say, look, okay, let's put it aside, maybe in the future, but for now let's do something else. I think that's actually a very, very scientific approach. So that's I really want to highlight, because I think there is a misconception around about what we are doing in our field.
Okay, and what about inflation? How can the standard model explain it? Because reading, let's say, to prepare for this interview, it arises the fact that let's say to match it with the standard model framework, we would need an inflaton. So a particle for inflation.
Exactly. So that also is like it goes back to what I was saying before. Also, inflation is in some sense an indication that the standard model is incomplete, right? So you have to have new particles, right, which also do inflation. So for example, the easiest theory for inflation is called a slow roll, in which is very simple in the sense that you have a new field, so new, call it particle if you like, right? Which is what you said, the inflaton. And this inflaton is basically driving this period of fast expansion that I was talking about. And then at the end of this period, this inflaton will also decay, for example, or in any case, produce the standard model particles, and then give rise to the standard cosmology as we know, right? Because we do need standard model particles, because then we have to create elements, hydrogen, helium, whatever, protons, to start with, right? So there is an addition also there. So you're right in the sense that also inflation typically requires people. So people, for example, have been trying to do inflation also with a Higgs field at high scales, and that in some case can still work if, more technically, there is some non-minimal coupling to gravity, it's called. But I would say that most likely you're right in the sense that people would need to introduce, and I work a bit on that, like an inflaton, which is an extra piece of the standard, beyond the standard model, also in that case. So, we have many, but this actually, I think that was this interesting, why I do what I do, right? We have many, many pieces of information that are telling us, look, guys, the standard model is not the complete theory. You have to look for something else. And that for me is very exciting, also very challenging, but also very exciting.
Okay, can I ask you again the name of the theory that you mentioned
for the Higgs?
No, for inflation. Slow roll.
Slow roll.
Okay, because I actually have not heard it. So, okay.
Yeah, slow roll is just a very simple theory in which you have a field. Slow roll it really means slow roll. So you have this field which is called the potential, and the slow roll this potential, right? And if you do that, basically you can explain the expansion. This field is dominating the energy budget of the universe at that time, and basically the universe is expanding during this phase very fast, and that's how you solve the typical problem of flatness, horizon problem, and whatever.
Okay. Also, just to make clarity, because sometimes I hear, let's say, not stories, but explanation, which puzzles me about inflation and the Big Bang. Okay, for what makes sense talking about time, but chronologically, was there the Big Bang and then inflation, and then the universe cooled down after some 1,000 years CMBR, or other way around, from inflation Big Bang?
So it depends what you mean by Big Bang, right? Also, how I mean the Big Bang, so the beginning of our universe, like heated up and then like cooling down, that's inflation happened first. That's a kind of like but it's semantic. If instead for Big Bang you mean the beginning of everything, right? Then you can wonder, okay, who put the inflaton there, right? Let's say, or whatever. But technically speaking, let's say for what I would say, there is inflation at the very beginning. So you start with this configuration in which there is this field in this potential that makes the universe expanding. Okay. Then at some point, this field stops slow rolling, and technically it means that it goes at the down of this potential, and it starts to oscillate. And basically, when it starts to oscillate, if it couples to standard model, we say that it will reheat the universe. So we'll basically transfer his energy, the inflaton energy, into standard model particle, right, with some given temperature. Okay, so this is why we call it reheat. And that's when is the Big Bang in some sense, and then radiation domination starts, and then we will have matter domination, and then we will have whatever, right? So chronologically speaking, in for whatever matters for our theory, we first have inflation, then we have this reheating phase, which makes start the cosmology as we know it.
Okay, and so here with Big Bang, you mean the hot, dense state of plasma of the universe?
Yeah, exactly. Basically, at the end, this state in which at some point you start to oscillate, you start to heat up everything and create this plasma, which is very hot and very dense and radiation dominated.
Okay, I have to follow up with a question regarding this. Inflation put before the hot dense state that we call Big Bang kind of leaves me with the bit in my mouth, because I then ask you, where was inflation embedded? Because then the question is not what was before the Big Bang, but why is inflation running? Because there are sort of inflation theories, for example, the eternal inflation, which they do predict an infinite kind of inflation, which creates multiple Big Bangs sometimes. So, and that's sort of a theory of a multiverse.
Yeah, but like the point also here is a kind of, again, is a kind of semantic, right? So there are some theory of inflation which basically they would even not work, in the sense that if you take a theory in which, for example, this field, slow roll, but then you have some quantum effect and you get kicked down and whatever. If you never arrive to the bottom and start to re-hit, then you never start the standard cosmological story, right? Then what can happen also is that, like you can have because of this inhomogeneity, is like different universe, right? Or it is also the motivation, or like the idea of the multi-universe, right? The multi-universe idea. But that doesn't, because like you can have configuration with different minima in your like field space at the very beginning, and each of these minima then would be in some sense its own universe, right? But that, in my opinion, doesn't really matter too much, because we live in our universe, that's it, right? And I don't know if it will be ever possibility to test other universe, right? What's a bit of a bitter in the mouth, like, is more, I'm not a religious person, but for sure we have a problem in that, we have to, some sense, like postulate or whatever, at the very beginning there is this inflaton, is there in its potential existence from forever. At some point you start to roll, you arrive to the bottom, and then everything starts, right? So I mean, then one can ask, this would be when religion, kicks in and start to ask, like, so I would like to kick in, right? I'm not religious at all, but and ask the question, okay, but who put there or what put there the info, right? That's, I think, that the most, I think that I would say that to never be able to answer. We just don't know.
Okay. Just talking about what do you think are the other pieces, let's say, of the whole universe, not only of our observable part? Do you believe the likely other universes are equally four-dimensional, or are they somehow, or they may somehow have different dimensions? Because sometimes when I think about it, but I also try to study some math and physics. It also, especially differential geometry, which is I think the first subject that you actually start to see some of this cool stuff. I mean, to me, it kind of seems kind of a little bit arbitrary, the fact that we have had four dimension, meaning that yes, we have four dimension, it works, but I don't really see I mean, at the moment now, I don't really see a reason why outside of what we can see is four dimension. I don't really see a specific reason why.
Yeah, I mean, like, the point is that, as we said at the very beginning, when we think about a theory, the theory always wants to answer experimental questions, right? And the experimental reality today, now, like forever, like for now, is that we live in four dimensions. That's it, right? So whatever theory has to start with that is the simplest possibility. Then, there are many theories which predicts extra dimensions, right? But it's not, for example, string theory, you typically have to have, I think, like 10 dimensions, 10, 11 dimensions in total, right? To have like a string theory. And also, as I was telling you, also typically also there are approach to the hierarchy problem that would predict extra dimension in which, we are embedded also, we just don't see it, right? Basically. So I think that is, it is a possibility. But also what I want to stress, and I think that we discussed this a bit also when in Amsterdam, like, people have been looking for that, people have been looking for new, for other dimension, right? And basically, because like the presence of other dimensions would typically modify the law of physics that we know. For example, if you imagine that there is another dimension in space that we just don't see because like it's very small or whatever, Newton law and, for example, the signal of gravitational waves in some case will be modified, or like Stafford colliders, you would expect to see something, you know, and stuff like that. So people have been looking for that, and we at this point we just have bounds also in that case typically. And the bounds means that if an extra dimension exists, for example, and is there, it has to be really, really tiny. Otherwise, we would have already seen deviation from the standard laws, which are thought in 3+1 dimension, right? So
Okay.
I don't know if it is, you know, in some theory, again, as you said, there is a motivation. Like in string theory, we know how many dimensions we would expect. But again, is that more motivated? I don't know, because to me, like when I think about the theory, it's always experimental driven. And at this point, we don't have experimental evidences of extra dimensions.
Okay. Okay. I would like now to move on to the next problem, which is the baryon asymmetry, meaning we see more matter than antimatter. What's this problem, and also what is the so-called baryogenesis?
Right. So that's another big problem, also another fascinating problem, and it's the fact, basically, the fact that we are doing this, you know, this chart, for example, is just thanks to the fact that we don't have the same amount of particle and antiparticle in the universe. Because if there would have been the same amount of particle and antiparticle in the universe, they would just continuously annihilate to each other into energy, basically. So we would not be here doing this interview, right? So the idea is that there is a huge ratio, like so difference between the quantity of matter and antimatter. And this difference is measured at very different scales. For example, when we measure also cosmic rays, we see an amount of proton over antiprotons, which is very large. So even like on galactic and extra, you know, and even larger scales. So the matter-antimatter asymmetry problem is just the fact that there is this huge, you know, like ratio between matter and antimatter. And typically in physics, when we see something which is very small or whatever, we always would like to have a dynamical or like an explanation for that, like a symmetry or a dynamical explanation. Why so? Because you can suppose that at the very beginning, you know, from whatever, like, you know, at the very beginning of the universe, there was just a huge asymmetry that actually at the very beginning should be even more between matter and antimatter. You can postulate that someone put there like this very huge asymmetry, that's it. You stop wondering, right? But you know, that's not how typically we think, right? We always want to find some motivation. We are not like satisfied. We just say, okay, whatever, there is this huge difference, that's it, right? So what we typically would like to do is that we would like to have a theory in which at the beginning you start to work from whatever situation you want, you know, order one, difference, symmetric, whatever, like, you know, very general condition between matter and antimatter, symmetric, for example. And then naturally, you know, in your theory, you produce this asymmetry, right? So this is what is basically baryogenesis in some sense. Baryogenesis is a mechanism that would dynamically produce from an initial condition in which you start after inflation, let's say with equal amount of matter, you would start to produce to basically to deviate matter and antimatter quantity, and you end up with this asymmetry, basically, okay? Is what is called baryogenesis. And what is nice is actually that mathematically, there are few ingredients that are necessary to a theory to have baryogenesis and to generate baryon asymmetry. For example, you need to have some, it's called CP violation, baryon number violation, out of equilibrium condition, right? And what is nice is that within the standard model, we do have all these conditions, okay? But that actually what is also interesting is that if you work out the math, they are not enough. So there are these conditions, but they would generate a matter-antimatter asymmetry, which is too small as compared to the one that we observe. So also in this case, actually, baryogenesis, matter-antimatter asymmetry, is an hint for the fact that we need more. We need some extra ingredient which would enhance these conditions and lead to the actual observed matter-antimatter asymmetry.
Okay, how do we do that? How do we account for this problem?
There are many theories. For example, one of the theories that is the most, in my opinion, appealing and exciting is called, it has the presence of new particles, which are called sterile neutrinos. And these sterile neutrinos, basically, they will be connected also to the problem of neutrino masses, right? But what is nice is that they also help to solve the matter-antimatter asymmetry. And how they do that, more technical, is that, you remember one of the conditions that I talked about was this like CP violation and also out of equilibrium conditions. If you have these sterile neutrinos around, which typically at the very, especially in the past, they were thought to be very high scale at the 10 to the 15 GeV or so. Basically, you add the CP violation because of some coupling of this particle. You can also have out of equilibrium condition when they decay. And then basically, this is one of the, at least in my opinion, very motivated theory to solve this. Yeah.
Okay,
but
so
there are many others, right? Like, there are others.
Okay. Would you bet your money on it?
I would say sterile neutrinos are pretty motivated. Yes, I would agree. One of the issues that I see there is that, especially the first theories, they were trying to put this into the context of what's called GUT, Grand Unified Theory. So typically, those theory would predict the sterile neutrinos, as I say, to be very high scale, 10 to the 15 GeV. So, like we talked before that the Higgs is around hundreds of GeV or so, right? So if you have particle at 10 to the 15 GeV, you can understand that it's actually very difficult to test this model. And so also in this point, I think that we are in a similar situation of something that I described before, is that I would bet my money that this probably is a very beautiful theory that could explain it. But I don't see any way to prove it in the near future if this is the case. But there are other theories that have been working on also, in which, for example, sterile neutrinos are lower masks. And that maybe we can prove with next colliders. But I would say that theoretically they're a little bit less appealing. Okay, but still they do their job. So it may be just a bias, right, that I have about beautiful whatever.
Okay, and now I would also move on to a problem relating neutrino and the mass. Why does the standard model predict the neutrinos to be massless, and subsequently why and how do we know neutrinos are not massless?
Yes, so that's another beautiful problem and puzzle. So first of all, I wouldn't say again like the standard model really predict the neutrino to be massless, in the sense that the standard model was built in a time in which neutrinos didn't show anything, to be, like to that any sign of masses, right? So the standard model was built to have neutrino to be massless in some sense, right? And there would be, like that with the left-handed neutrinos, that was enough to describe the world as we knew, right? So in some sense, it's not, I wouldn't say it really is a prediction, right? It was just the theory worked very well with these ingredients, right? Left-handed neutrino, massless, you could explain all the experiments, that was beautiful, right? Then what happened is that basically we started to see oscillations of neutrino flavor. Okay, when you produce some neutrinos, you will produce it in what they are called like interaction eigenstates, right? So basically, and the flavor means electron flavor, muon, or tau, right? Because they arise with some kind of interaction, and they interact in such a way, with leptons, okay, with leptons that are electron, muon, and taus, right? But then, one of the first problems was actually that people in the United States, like at the IES in Princeton and others, experimentalists, they measured the neutrino flux from the sun, and they did some theoretical calculation to predict basically the flux of electron neutrinos, and then they were basically missing a factor of 1/3 in what they were observing. So for a while, people told them, look, you just don't understand the sun, your calculations are off, whatever, right? And then the resolution of the puzzle come afterwards, when people could really measure the oscillations. But just the fact is that if neutrino have masses, you actually do expect that if you start, imagine that I produce a neutrino in the electron neutrino state, right? This eigenstate, okay, doesn't coincide with the propagation, with the mass state, right? So basically, in technically speaking, in technical details, there are two different bases: the base of interaction and the mass basis, right? And they do not coincide, right? So if you produce, and every state, imagine that is a complete basis, right? Like you may know from geometry, every state, let's say in one basis, right, will be written down as a combination of the other bases, right? So if you produce a neutrino in the, say, like the electron states, right, it will be a combination, right, of the different mass eigenstates, right? And so basically so when it propagates, it will propagate as a combination of those, right? And you will feel also different matter effect and whatever, right? So it will propagate also with different, every state will propagate differently depending on the difference in masses. And when it arrives on Earth and you detect it again so collapsing it into interaction instead, because you have to interact with it to detect it, right? Then it will show a different ratio of electron, muon, and tau, okay? And actually, if you ask enough time to propagate, basically, it will typically show the same flavor, the same ratio of electron, neutrino, electron, neutrino, muon, neutrino, and tau neutrino, right? And this was how we knew that actually that deficit, that 1/3, was basically due to this. That state that you produce in the sun, it didn't stay the same because it propagated, and so it was a combination then. And then it propagate, whatever, and then you arrive on Earth in such a way that basically is 1/3, 1/3, 1/3, and that so when you measure electron neutrino, you measure 1/3 of what it was produced, right? For example, this was how they explained it. So, but basically the oscillations of neutrinos is how do we know they have a mass? Is actually just to say, like, it was like this. Few people got awarded the Nobel Prize for neutrino and neutrino masses related stuff. So it's a very important deal. And actually it's nice the fact that I spoke just before about sterile neutrinos, because one of the reasons why I think that actually that theory that I told, the sterile neutrino, very massive one, is a beautiful theory for baryogenesis, is that incidentally, with that, you also explain why neutrino have masses and why neutrino have such small masses. And basically it's the fact that when you write your complete theory, you will have your left-handed neutrino, you will have your sterile neutrinos, and then at the end of the day, the interaction between these, works out in such a way that even the neutrino that we know, so not the sterile neutrinos, they acquire a small mass, right? And why small? Because basically at the end of the day, you remember that I told you these sterile neutrinos are very massive. The way in which this stuff works is that at the end of the day, mathematically, the mass of our neutrinos, the one that we know, will pick up a 1/, the mass of these heavy guys. So this is the so-called seesaw mechanism. Seesaw because it works really like a seesaw, right? So the larger is the neutrino, the sterile neutrinos, the smaller will be the mass of the neutrinos that we see on Earth, that we see in our actual experiments, right? And I think that is a beautiful theory because with the same particles, sterile neutrinos, you explain both the neutrino masses and why they are so small, and two, also the baryogenesis. So this is why I would bet on that, right? So
yeah. Okay. Can I ask you why do okay? So basically, said that from the sun emits this neutrino. They are a combination of eigenstate of mass. This combination through the journey changes, and why does this imply that neutrinos have masses? Why this change of combination?
No, because the combination depends, like the mass basis is, is a mass basis, and every, you also imply that the neutrinos masses are also different, because like actually at the end of the day, all this the change in stuff depends actually. So the final ratio that we get on Earth will not depend actually on the single masses. Will depend on if they were all equal, you would probably not notice, right? If there was too small of a difference. The crucial part is that we know they have like masses, and the difference, at least among two flavors, is non-zero. Okay, and this observation is crucial. So, and is the easiest way to explain not only the sun, but even you can do other experiments in which you can control things more easily, like in the lab, right? In the United States, for example, is investing a lot in this. Japan, same, right? And try a little bit to produce neutrinos, to make them propagate along some long baseline and measure them, right? And so if they have masses, okay, how they would, like say propagate. You can go and measure the ratio that you see and see if you agree, right? And that's what happens.
Okay, I understand. So the theory you proposed is the proposal you made is the one you would bet your money on, I guess.
Well, that is a very, very interesting theory, very beautiful also because typically, like you will need some partner, the left-hand particle typically will have some right-handed partner, which is the sterile neutrinos in this case. So you explain also baryogenesis. So I think it is beautiful. And but again, maybe I'm biased because I've been working also on that. But I think it is elegant. You know, you just have another addition. That's it.
Okay. Now I would like to ask you, what is the CP problem? You mentioned it before. What is the strong CP problem?
Exactly. The strong CP problem is another interesting issue of the standard model. So now we are accumulating a lot of issues, right? And is the fact that basically strong interaction, so the strong interaction sector is he has at the technical level, there is some in your Lagrangian that I already mentioned at the beginning, there is some operator, okay, which violate in the strong sector. So it's some term in the Lagrangian, okay, which violates what is called CP symmetry, okay, which is a symmetry which is basically related to charge conjugation, the C, right, and parity symmetry, okay, so the CP symmetry. Okay? Now, in the QCD sector, there is an operator that actually violates this symmetry, okay, and that actually experimentally predicts an electric dipole moment for the neutron. Okay, you can do the computation. It's something that also Witten have been working on, like in the time. And basically, you predict an experimental fact, an electric dipole moment for the neutron. And you know, when I say a term in the Lagrangian and stuff, there is some coefficient in front of because it's a term in the Lagrangian with field, which are called the gluons, and a coefficient. Let's call it theta. Okay. Now, people went in the lab and they tried to measure this electric dipole moment for the neutron. Up to now, we don't have a measurement. We just have bounds. Because if an electric dipole moment exists, it has to be tiny, 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 because no one detected it yet, right? So basically, what this tells us, it gives us a bound on the parameter of the Lagrangian, right? Of the term that I was talking about, this theta that I just introduced. And basically, the actual situation, experimentally, is that this theta parameter has to be smaller than 10 to the minus, roughly 10 to the minus 10. Okay, so it's an extreme, because otherwise, if it would have been larger than this, we would have already seen an electric dipole moment of the neutron. Instead, we didn't see that, so we just know that theta has to be smaller than some value, because otherwise, would have been different. And so we basically now have a parameter, this theta parameter, which has to be smaller than 10 to the minus 10. And then, as I told you, like already a couple of times, when in physics, typically when we see these like super small numbers, right, without a reason, we are puzzled a bit, right? And of course, you can say, okay, it's 10 to the minus 10, that's it, right? You don't care, right? But we would like to understand why so small, right? Why we don't see an electric dipole moment of the neutron, right? And typically, in some sense, philosophical or like conceptual, if you want, is very similar to the inflation problem, right? In inflation, if you read about something about it, right? How it was motivated? It was motivated by this flatness problem, right, and the horizon problem. And the flatness problem just is really a problem about small quantity, right? The universe has to be like needed to be very, very flat at the beginning to explain the observation today, right? And this was not satisfying. It has to be like 10 to the minus 50 in terms of some small like adimensional parameter, right? We just were not satisfied. So what we created was a theory that dynamically explained why the universe, like when then was flat. So there is this expansion, and you have prediction for the theory, with the CMB and stuff. And the same thing in the theta parameter. It's a small parameter. We will have to have symmetry, a dynamical explanation for it, right? That's why for us is also very interesting lately. And one of the most appealing theory, in my opinion, but not only my opinion, is the axion. Because what happened with the axion case is that basically you promote this theta parameter to a field, a particle, which relaxes to zero dynamically in a potential, it's called. Okay, so basically, once again, what you do, you solve the problem because you have a symmetry behind, you have a dynamical explanation, you know it, and actually now you also have prediction because you know that if this is the solution to the strong CP problem, you have to see at some point this axiom. And what is extremely interesting is that I told you in the first part of the interview, incidentally, by chance, this axiom also turns out to be a very good dark matter candidate. So that's also why, in my opinion, makes this even more appealing, right? And this kind of like close the circle, right?
Okay. Can I ask you,
Yeah.
what is the CP symmetry?
Yeah, the CP symmetry is this combination. You have to respect, like this C stands for charge conjugation. Okay, so like just exchange a particle to the antiparticle, basically. P is parity, just like a mirror symmetry kind of, right? So CP is the combination of these two symmetry, okay? And you have to, you can either respect or not respect that, okay? What is actually typically when you do you remember that I talked about quantum field theory. What is typically a symmetry of a quantum field theory to be a consistent theory is the so-called CPT, okay? In which you have CP and you also have time reversal symmetry, okay? Like a process will look the same, like if you invert time, basically, right? So CPT has to be conserved, okay? So this means that if CP is if CP is conserved because this theta parameter is small, right? This also means if CP is if CP is violated, let's say, to conserve CPT, you have also to violate T. So you can see like violation of CP, like also violation in time reversal if you want. Okay, because like imagine that you have CPT, you have to conserve all of that, right? Because CPT globally is a symmetry of quantum field theory. Then if I violate CP, I also have to have violation of T. Otherwise, I would violate CPT in total, right? So you can see a violation in CP to also a violation just in time reversal if you want.
Okay. And so basically you mentioned that here you would bet your money on actions to explain this problem. But now that we are wrapping up this problem, which is the proposal, the theory that encompasses most of the problem we mentioned, or do you just believe, well, we will not just adopt one theory, but we will just adopt many extension of it. We will extend it in multiple and different ways, just trying to encompass all of these different problems.
Yeah, so like at the end of the day, like I think that at this point, for what I think that the likely thing is just that there are different particles which are just different problems. For example, a theory which would solve most of our problem. Let's forget about inflation because that is a kind of detached to then the universe. Imagine inflation has to have some inflaton. That's it. Okay, let's forget about it. But then let's say we want to explain also the universe today, like the measurement today, right? Neutrino masses, dark matter, whatever, right? Then you can add sterile neutrinos and you can add axion. And in that way, very easily explain baryogenesis and neutrino masses, dark matter, and the strong CP problem. For example, that's a kind of a minimal extension if you want. In some sense, neutrino and axion do not talk, or maybe they talk, but we don't introduce them to get like we introduce the axion to solve some problem, the sterile neutrinos to solve some other problem. That's it, right? So, and that's already like a theory which explains a lot. That's of course like that has to be tested, right? There are theories in which actually you can try to solve even more problems at once. For example, there are some theories in which you have multiple sterile neutrinos. Some of it actually can make dark matter. So within a theory of sterile neutrinos, you can explain baryogenesis, neutrino masses, and dark matter, for example. But then you still are left with the strong CP problem, for example. I think it is just a matter of like what you think is more likely, and then wrapping up is really a matter of experimental evidences. Experiments will have the final word. If we find the axion in some of the experiment that we are looking for, then amazing. And then we can worry about sterile neutrinos and neutrino masses for something else. But I would say that when we think about a unifying theory, it's just, for me, it's always a theory which explains the universe. And also, like, it's true that I mentioned multiple times during this interview, elegant, beautiful, whatever. But my approach is also that I'm always kind of driven by experiments and stuff. And at the end of the day, true, you always start with a simple theory, right? And then you make modification, right? But as long as the theory explains something that someone else cannot explain, then experiments should judge if it is correct or not. As I told you, like Weinberg didn't believe his theory was the correct one. He has too many parameters in his opinion. At the end, nature works that way.
Okay.
So I think that we don't have to be biased. Yeah, that's what I want to conclude with.
Okay. And picking up on the parameters mentioned by Steven Weinberg, what do you think? This is, let's say, more of a fundamental question. Why, actually, how many parameters we have in standard model overall?
Yeah, that's a good question. I don't know. I do the counting because we have many, because we have all the Yukawa couplings of the particles, the web of the Higgs, and I will get the gauge couplings. I will count them down, but they have few, few of them.
Okay, around at least some
More than
dozens.
10, more, yeah, exactly.
Okay. Okay. What do you think? And so, I mean, all of these parameters have values which we have experimentally validated. What do you think is the meaning of these values? Are just the brute, elegant testing of our experiments, or what do you think these values? Why do you think these values are the values they are?
Yeah, I mean that's a fundamental question, but like, so for my kind of approach, typically I would start, like in quantum field theory, we also have a criterion to understand if a value of a parameter, let's say, is okay or not, right? It's the fact that, imagine that you have a parameter, and then what you can do, you can in quantum field theory, the constant of our standard model, they are not really constant. They depend on energy, right? And so basically you can do what is called, you can run this parameter to high energy and see how they look like, for example. You can also add correction, loop correction to this parameter and see what happens. So what we typically see as a good parameter is a parameter for which, if you apply loop correction, okay, what I told you at the beginning, like you put particle in loops and stuff, you don't spoil that parameter. Because if you do spoil that parameter, if you imagine that like with the mass of the Higgs, then the parameter to be what you see is a tuning. Because like if you would have not, because like imagine that you have a parameter that is a measure, but then that you measure, okay, and then you would say that is the parameter in your theory, okay. But then as soon as you start to compute the correction to that parameter, just coming from the fact that that particle interact with other particles, imagine that the value that you get is completely different than the value that you measure, unless there is some very precise tuning among quantities, right? Or like stuff like that. So in that case, we will not be satisfied and we have to find an explanation. But typically, if parameters are order 1 or 10 to minus 2, 10 to minus 3, whatever, like value, right? As long as they don't have inconsistency with the theory, then it can well be that it's just a parameter. For some of the parameter, for some of the constant, we also have kind of anthropic reason. For example, one of the parameter which is also like a puzzle is the dark energy. The dark energy, like is the fact that it's very small, okay? But if you compute the contribution from particles to this dark energy, right, basically you end up having a very weird situation in which you would not expect the dark energy to be as small as it is, right? But for that, for example, we have an anthropic reason to believe that that we have to live in a universe like that, and disconnect in some sense to what you were mentioning about multi-universe and stuff. Because if you would have imagined, if we would have ended up in a universe with different parameters, a different dark energy, right? Just we would not do in this interview because the structure would have not been formed or whatever, right? So there is also kind of an anthropic reason. Some people don't like, because it's like, that's it, you accept it, you don't have to explain anything, you cannot do science on it, right? But on the other hand, for some parameters, they do have an anthropic reason, and Steven Weinberg wrote a very famous paper about the anthropic reason for the cosmological constant, actually. And so for some parameter, I would say, to reply to your question, so in general, we like parameters to be what they are if this is consistent with our theory, in the sense that if we do loop correction and stuff, this value is not screwed, right? That's what we typically have as a guide, guidance. We don't want to be like super small and fine tuned, because otherwise it will be very, like also odd in some sense, and easy to perturb them, right? As I said. And third, for some of them, there is an anthropic reason. So for some of them, it would be, okay, maybe it could be different, right? But if it would have been different, we just would not know, because we would not be here to observe it.
Okay.
right?
Andrea, is mathematics invented or discovered?
Mathematics invented or discovered, and I think it is. I would say, but just again, I think that sometimes it's semantic. I would say it is discovered,
Why?
and in the sense that until like until now, at least in relation to the physics, right? To the physics world that I'm more familiar with. What happened now? What has been happening, like in physics, is that it happened few times, multiple times, I would say, that you would discover a physical phenomena for which you would need a certain type of mathematics and mathematical structures to be explained, right? Now, in some cases, that mathematical structure was already there, right? And we indeed like just discovered that there was a description of our physical phenomenon. For example, this was the case with the Gell-Mann and all the theory of quarks and the standard model in general with SU3 and SU2 and whatever, right? And the octet of SU3 actually, how you position the particles. It basically didn't know all this, like it's based on group theory mathematics, right? And it was something that was already like developed, but it could have been the other way around. You would have made the discovery, and you would have been forced actually to discover, to unveil a mathematical structure there, and then you would have find out that like there is some properties and some stuff. And in that case, I guess that what I mean by discover is really the fact that there are some physical and logical structures for which you would then associate a mathematical structure. And so in that case, this is discovered in the sense that in some sense they were already there, right? This physics, this was already there. Then you have to unveil the structure and to create the rules, right? But in some sense was already there because the physics was already there.
Okay.
So, but I guess that is also like semantic, and but similar things happen in multiple. Also, Witten discovered mathematical structures thinking about physical problems, like in string theory, for example. So, but yeah, it's an interesting question. I would think more about that.
What do you think is the difference between mathematics and physics?
Well, there is a very huge difference. So I love mathematics, and I think that like physics needs mathematics, and but at the end of the day, physics is really natural. Is the most important, I would say, natural like science in the sense of Galileo, right? Like in the sense of like experimental method. You do a theory, you do an experiment, you confirm that. Right? It's really the essence of the experimental method. Mathematics, you don't need a real experimental validation, right? You can create beautiful pieces of mathematics just through consistency, right? Then at some point you will probably find out that you describe something in nature, right? But that's a bit different, right? Typically how physics work instead is that you want to explain something and then you invent your physical theory. In mathematics, a lot of time you just start from consistency, right? And logic, and try to, especially now, right? In the past, probably with geometry and stuff was a bit also more practical. But now you really have also branch of mathematics which are really, really abstract, right? And for now, they have not whatsoever application with the real world, right? But in the future, I'm sure they will.
Okay.
That's a big difference. Experiments, yeah.
Okay. And one last question: when do you do your research and you work on on your on your stuff? Let's say you try to unveil the inner working of our universe, how things really are. What do you think the underlying meaning of these all mean? Because, and I explain, sometimes there are some sort of fine-tuning problem in some specific theories, but I can think that also overall, from our overall perspective, in our universe, for complexity and intelligence life to arise, a lot of things had to go a certain way. What do you think is the meaning of a bunch of matter coming out of a plasma forming complexities, ultimately species that could auto-reproduce themselves into our civilization.
Yeah, but that I think that connects pretty well to the anthropic reason that I was telling you before, right? And there are some parameters which have this anthropic reason in the sense that things had to go in some way in order to have life and to develop whatever, right? But for other parameters, there is no anthropic reason. In other words, there are some parameters, like for example, some is more like some of them are more tricky, but there are some for which, like the cosmological constant. Some people argue also the web of the Higgs, for which basically, if they would have been different, you would not have life, for example. For example, you change some parameter, then you don't form, let's say, supernovae, and then supernova, or like they are different, supernova, they don't produce heavy elements, so you don't produce heavy elements, and then you cannot have life, right? For example. But there are other parameters for which, and I think that, for example, the theta parameter of the strong CP problem, I've been trying to think about it, but I think that is one of them. There is, in that case, no anthropic reason, in the sense that the theta parameter could have been, or like no easy anthropic reason. I mean, let's say this parameter could have been whatever he wanted in some sense, not 10 to the minus 10, maybe 10 to the minus 5, right? And things with life and stuff would have been evolved as beautifully as they did, right? And so that also posed the question, maybe the two things are just disconnected. So there are some parameters which are related to that you say. I agree with you, like, in order to have life, we have to end up in a universe that looks like our universe. We know that. And for the only knowledge of life that we know, and maybe there is some other kind of difficult stuff, but for the knowledge of life that we know, we have to end up in a universe that looks like the one in which we live, right? In order to end up in a universe like the one in which we live, some parameters needs to be in a certain range, because otherwise we would not. But other parameters, they don't seem to be related to that. They could have changed widely, and we still would end up in the same life-friendly universe, right?
Okay.
Yeah.
The anthropic reasoning sometimes leaves me with some bitter in my mouth, because I wonder, okay, but this anthropic reasoning does not prevent any other possibility from happening anywhere else.
I agree.
That's something I
but this is one of the, for sure it's something that, you leave you a bit, but on the other hand, if you believe, it is true, right? If you believe, you say that it's not, we are asking what we are asking just because we live, right? So then if the parameter that you're wondering about, is not correct, you will not be here asking this question, so you lose meaning, right? But I agree with you that in this process, the point also of all this, a lot of people why they don't like the multiverse and stuff, right? In other universe, the cosmological constant could be whatever. But then there will not be, another Francesco and another Andrea doing an interview, because, things would have crashed before, or expanding too fast or whatever, right?
Okay. So I think we can wrap it up here. Andrea, thank you very much. It was extremely pleasant. And again, thank you for your time, and I wish you the best of luck.
Thanks a lot. Thanks for having me. And, I'm sure that we will chat again and have some other fun. It was a pleasure for me. So, yeah, talk to you in the future for sure. Again.
Thank you, Andrea. And yeah, thank you everyone for following along with us. This was Math and Beyond, and I will see you in the next episode. Ciao.